All right, folks, it's Bass Action, back in action here. In this video, we are going to look at what is called instantaneous rate of change. Now, we've already discussed, and I don't have it filled out in this particular slide, but we've already talked about average rate of change, and you can actually see it here in the image that I've got. Our average rate of change is, we can see that the rate of change of this actual curve, this blue-purple curve here, is changing depending on where you are. But if we connect 2 points, and we can look at that as an average rate of change. What we want to do in this video is look at instantaneous rate of change. So what would be the slope of at a single point? So if these 2 points were moved closer and closer and closer together, what would be the rate of change when they became so close together that we couldn't actually tell the difference, okay? So when we look at this description here, you can see that it says that we're going to use the difference quotient to determine an instantaneous rate of change. And I'm going to show you the difference quotient over here. Okay, and what we'll do is we'll use smaller and smaller values of h. So this value right here will become something so small that it effectively will be 0. And you can see I've got that right here. So when our h becomes so small that it's effectively 0, the slope of the line will actually be tangent to our graph instead of the secant line. So instead of having a line that looks like this red one, we'll end up with one that looks more like this right here, okay? Now, what we're going to do is we are going to come over here and we're going to find our difference quotient. And there's a lot of algebra in here, and this is why we've been reviewing our function operations. So the difference quotient has a couple parts to it. We are going to provide this to you, and for those of you going on to calculus, this is actually where your calculus classes are going to start next year. So the first thing we're going to start with is this f of x plus h. So remember that means that we're going to replace the x's with an x plus h. So this is going to become a negative 2, and then I'm going to have x plus h, quantity squared, and then my plus, and then it's going to be another x plus h because all the x's have to replace with x plus h. And then I'm going to subtract the entire f function. Now these parentheses, this parenthesis that I wrote right here is really, really important for us. So we're going to write that parenthesis, and then we're going to write this negative 2x squared plus an x. This entire expression here then is going to be over an h. Now, don't forget to keep writing that over an h. I know it gets kind of annoying on these, but you're going to want to do that because otherwise students typically forget that it's still supposed to be there. Now, the goal of these difference quotient problems is actually to ultimately be able to cancel this h. So if this h in the denominator doesn't cancel when we're done, then we've done something wrong. I like to do a little bit of a rewrite up here, okay? So I know that when I FOIL this x plus h quantity squared, I'm going to get an x squared plus a 2xh plus an h squared. I just like to rewrite that so I don't have to rewrite everything else in my next step. Then what I'm going to do is I'm going to remind myself that this negative needs to distribute to everything. So now I can take my negative 2 and distribute it to all of this blue. And that's going to give me a negative 2x squared minus a 4xh minus a 2h squared. Okay. Plus, I still have that x plus h. And now when I start to distribute, I'm going to get a plus 2x squared minus an x. And this whole thing is still over h. Now, at this point, we should be able to cancel everything that everything that is just an x term. So sure enough, we have a negative 2x squared and a positive 2x squared. So those are going to cancel nicely. We can see that we have a positive x and a negative x, and those are going to cancel nicely. Then we are left with this negative 4xh minus 2h squared and this plus h. I'll be honest, this plus h gets lost a lot for students. At this point, everything that I have left has an h in it, so I'm going to factor that h out, and I'm going to be left with a negative 4x minus a 2h plus a 1. Be really careful to not lose that plus 1 all over this original h. And just as I said we wanted to do, those canceled. So our difference quotient is this expression, negative 4x minus 2h plus 1. Now in the next step, I'm going to show you how we're going to use that expression to find this instantaneous rate of change. All right, so we're going to hold on to that, and in the next step, what we're going to do is we are going to find the slope of the tangent line. This expression here is going to be used to find the slope of that tangent line. So we're going to use this directly in our next step down here. What we want to do is we want to find the point 2f of 2. Now remember, f of 2 is going to be the y-coordinate when we substitute 2 into our function. And then remember, our function in this case was f of x, and it was a negative 2x squared plus an x. So if I substitute 2 into that function, and I find my f of 2, I am going to get f of 2 is going to be a negative 2 times my 4 plus my 2, or in other words, a negative 6. So the point 2f of 2 is actually the point 2 comma negative 6. Then we're going to let our h value be something really, really, really tiny. Now, because that is 0.0001, it's so small, this is effectively 0, which means we get to pretend it's 0. So when we take our values and we substitute into this expression here, we are now going to have a negative 4, and the x value is supposed to be a 2. We can see that both because it says x is 2, but it's also this 2 right here, the same 2. And then since the h is so tiny, we get to pretend that it's 0. So we say minus 2 times 0, and then plus 1. And then we simplify that whole thing out, and we're going to get a negative 7. Okay. So then when I get my negative 7, oh, I just caught my little tiny error, and some of you guys probably already saw it. This was a plus, and I wrote a minus there. Let's get that fixed right away because I had the right answer, but it didn't make sense for what I wrote there. So I have a negative 8 and a positive 1. That's where I was getting that negative 7. I didn't catch that I had written that wrong. Now, this negative 7 is going to become the slope of our line, and this is a really important detail. So places where students often struggle, as I mentioned, they lose that 1. They don't realize that this number is effectively 0, so when you substitute in, that can become 0 right there, and that then your resulting value is going to be the slope of your line. So now, in terms of writing our line, we have our point and we have our slope. We have the two things we need to write the equation of a line. You can see here again, this is going to be the same point, 2f of 2, which is the point 2, negative 6. And then when we go to write our line in point slope form, we can say y plus 6, and I'm going to say negative 7 and x minus 2. And if I want to clean that up, I can go ahead and rewrite that in slope-intercept form, and it would become y equals negative 7x plus 8. Now, when we go to graph this, what should happen is if we graph this line on this grid, because this graph right here is the graph of our function y equals negative 2x squared plus x, okay? So this is the graph for this parabola, and if we graph this line, it should be tangent to our graph at the point 2, negative 6. So let's find our point 2, negative 6, and I'm going to put that right there. And if we want to graph this, what we're going to do is we're going to use this slope-intercept form, or really just our slope. Since I can't see this y-intercept way up here of an 8, I'm going to start with my point, and I know that my slope is supposed to be a negative 7. So from my point, I can go up 7. So I'm going to go all the way up 7, and then I'm going to go back 1, because it's supposed to be a nice negative slope. So that's going to give me this point right there. Now mine's going to be a little bit harder to draw here on an iPad, so I'm going to do my best. But you have probably a nice straight edge there, but this is still pretty good. If I connect those 2 points and we look at this, sure enough, the line that we just created the equation for does in fact look tangent to our parabola at that single point. So this is called our instantaneous rate of change. And again, for those of you going on to calculus, this is where you are going to leap and start your calculus life. But for us, we're just going to get comfortable writing these equations of these lines and working with our difference quotient.